Yes, I invite Professor Indranil Mazumdar to give a talk on the free body systems. Actually, Professor did see in, and then he joined the in nuclear science center for his PhD. He did his PhD under this joint supervision of KP Sinha and myself. And after doing the PhD, he joined the Tata Institute of Fundamental Research, where at present he is a full professor in this. He has been in contact with me for so many years, and we have been jointly working on the research problems. He will be talking on the free body systems. I invite Indranil Mazumdar to please give a talk.
Good morning, everybody. Thank you, Professor Haseen. Let me just begin by putting on record my sincere thanks to the organizers, especially Professor Alok Mishra and Dr. Gargi Mishra Delmont for their kind invitation. Just one sentence here before I start the talk, that actually there is a change. I mean, the title of the talk is To Fuse or Not to Fuse, A Tale of Two Nuclei. It is actually heavy ion. I'll be drawing today from my work on heavy ion nuclear physics. So Professor Ashok Nath Mitra was a towering figure in the world of physics in India with an enviable degree of international recognition for his many accomplishments. He was one of my most venerated teachers, and I had the good fortune of enjoying his affection and encouragement from my student days till his last. Now, let me tell you about why I selected this topic for today's talk. A significant portion of my research activities in nuclear physics is centered around studies in structure of exotic halonuclei and search for the elusive Efimov effect. As Professor Haseen just mentioned, we use a three-body model of the nucleus, which is two-neutron halonucleus, using separable non-local interactions. The use of separable non-local interactions in three-body nuclear physics was truly pioneered by Professor Mitra, and along with his very able students that time. One of them is the chair of the session. So ideally, I should have chosen to talk on halonuclei and Efimov effect. However, the research interests of Professor N. Mitra was a rather broad canvas. And though he was not truly a practitioner in structure and reaction of nuclear physics at the low and medium energy, he always kept himself abreast of the developments. And even as late as 2009, he actually wrote a wonderful piece, India in the World of Nuclear Physics Then and Now. And if you go through that article, you will know that he was totally in command of whatever was happening in the low and medium energy nuclear structure and reaction studies even at that time. And which is why I decided to talk about my activities in heavy ion physics and present you some very recent results, though the work is going on for last at least 2 decades. I'm sure that Professor Sar would have been very happy and enjoyed the fascinating world of heavy ion nuclear physics. Now, the very varied nature of the audience and the time limit do not permit me to go into the nitty-gritty details. Rather, I would just like to give you a flavor of what we are doing, what are the real burning issues. And this is a very hot topic in current nuclear physics. So it's basically going to be some kind of a storytelling. So this is basically the organization of the talk, prefatory comments right in the beginning, why we are so much interested in this problem. And this is primarily an experimental work, which will probably be a slight change from all the talks that you had yesterday and also later in the day tomorrow, today. It is a primarily experimental work, but we carry out very heavy kind of phenomenological calculations for the analysis. So I will briefly talk about the experimental facilities, the very simple-minded facilities that we have at our disposal. I'll give a brief summary, very brief summary of the last decade-long studies from a collaboration between TIFR, my group, and our group from Indranil University Accelerator Center. And then I will draw from 2 very specific cases, 2 very recent papers, and then I summarize and conclude. So basically, as you know, the 60s, as I can say, was the best of the times for nuclear physics. It was also the worst of the time, or rather, the time of our innocence in nuclear physics. So heavy ion physics was not really there in the horizon. It all happened with pioneering experiments of David Bromley and his collaborators. So basically, they did their measurements shooting carbon-12 nucleus on carbon-12. And they really didn't have anything specific in mind. They just had a machine they built, and they wanted to test it with heavy ion beam, which was not available those days. So they were expecting certain kind of results, but lo and behold, what actually happened, they saw distinct resonance structures, as you can see on the right side of the panel. And these basically, when this was analyzed and understood primarily by the theorists some from US and some from Germany, by Walter Greiner's group, they realized about what actually is happening. And in a sense, the experimental discovery and theoretical description of nuclear molecule led to the development of the modern heavy ion physics. So now this particular plot is very, very important. So what actually we are doing, this is for those who may not be involved at all in heavy and medium energy nuclear physics studies. So we want to understand the real-time response of the nucleus at hot and rotating nucleus to an external trigger. And this is basically done by shooting a heavy ion on another heavy ion, as you can see on the right side, this pictorial depiction. And then many things can happen. It can undergo an elastic scattering. It can undergo a mild inelastic scattering. It can undergo some kind of transfer reactions where few nucleons can be moved from one side to the other. Or it can just, as you can see in the second part, it can just form a dinuclear system, which may rotate a bit and then fragment immediately. This is what is called quasi-fission. But it can actually fuse and form so-called the mononucleus, which, because of a critical angular momentum, doesn't really see the barrier, which has vanished at that angular momentum, and split immediately. This has been termed as fast fission. However, if the system fuses and survives this fission and fully equilibrates in all degrees of freedom, then two things can happen. The system is now inside the pocket of the potential well in the potential energy surface, and then it can split into two parts, which is called fusion followed by fission, or the system can survive fission, and it's a hot system, so it will evaporate few particles and shed all its energy and come down to its ground state. So what we have there called the evaporation residues. And if you detect experimentally evaporation residues, you know the system has survived fission. That is the moot point, actually. So the important thing in the analysis is the dynamics of the formation, dynamics of the decay of the system, as I just said right now, evaporation of particles or fission. And then in the analysis, you actually have two-pronged approach. You have to have statistical theory. Without that, you cannot do anything. You cannot find out how the particle evaporation is happening, etc., which is governed basically by phase space, Bohr's theory, and also governed by the nuclear level density. However, dynamics is of paramount importance, so we also have to do dynamical calculations. Mind it, nuclear fission, to do it fully microscopically and considering quantum mechanics, everything is a horrendously difficult task, and the task which is still in progress. So we basically try to take a middle path of a mixture of microscopic, macroscopic approach. Now, the major challenge in the physics is that in this talk, I will be concerned only with the fusion followed by fission and try to see if the system survives fission. But even if you talk of the fusion, you will see there is physics all along the energy scale. If you are below the barrier, where classically you do not expect the system to fuse, it still fuses. And it is much more than what you would have imagined from simple model of simple calculations of barrier penetration, tunneling. Because there are lots of quantum mechanical, this is a quantum mechanics, a lot of channels gets coupled, and this channel coupling leads to the reduction in the barrier, and that leads to the fusion. But if you go to even below the barrier, very, very below the barrier in the region of nuclear astrophysics, there, of course, these couplings gets weakened, and you see much lower fusion. And of course, in my talk and in my own research activities, I am principally involved at a fusion much above the barrier to understand the hot nucleus. So the equilibration and the stability of the compound system, what role the shell effects are playing in this, and the role of complete and incomplete fusion. This is very important as far as our own results are concerned. Role of entrance channel mass asymmetry. If you produce the same compound nucleus by two different target projectile combinations, by the classic Ghoshall's experiment, you may tend to believe that the system will decay exactly in the same way, but they do not do that. So there is a role of entrance channel definitely, and the role of nuclear level density, barrier height, the fission barrier, which is definitely a dynamical quantity, depends upon the spin and the temperature, and the nuclear viscosity. So basically in our work, we have been involved to understand this dissipative mechanism in this heavy and induced fusion fission processes. So the primary motivation is, of course, twofold. One is to understand the dynamics of the fusion and the subsequent fission or survival against fission. And the second, which has always been the holy grail of nuclear physics, the quest towards the formation of super heavy elements, because you want to form a very heavy system, very high Z value, but it will fission. So if you know somewhat at the lower masses, what is the dynamics, we can plan for super heavy elements. So experimentally, this is achieved by measuring the fission fragments. Since it is fissioning, you talk about the fission fragments. Then we measure the evaporation residues, and we measure the charged particles, we measure the neutrons and GDR gamma rays, which is giant dipole resonance gamma rays. And once we get the data, we analyze it. And in that analysis, we basically try to see how the nuclear level density, the shell effects, the entrance channel masses, the target projectile deformations, the barrier heights, which is spin dependent and temperature dependent, and the nuclear viscosity, and above all, their dependence on temperature and angular momentum. So basically, these two slides sum up what I want to do. Now, nuclear fission, as you know, is an evergreen process. It is basically large-scale mass transfer across a barrier in a dissipative medium. And it's a very, very complicated process. Either you study through microscopic analysis or you try through microscopic analysis. But basically, a middle path has been struck, which is microscopic plus macroscopic. And here are some of the important references, but not exhaustive. So let me just give a quick glimpse of the experimental facilities. As I said, the system is primarily fissioning. So fission fragments detection, that will be low-hanging fruits. So we have fission fragment detectors all over the world. People have charged particle detectors, neutron detectors, high energy gamma detector, giant dipole resonance gamma detector. In the early days of my work during Stony Brook, my postdoctoral days, we measured a lot of high energy GDR gamma rays, giant dipole resonance gamma rays from a fissioning system. But the difficult challenges are to measure the evaporation residues. This one has to appreciate and understand, because the system is primarily fissioning. So you have to filter out those which have survived from the main beam particle and detect and measure their cross sections. At the same time, since it is all about the game, about how things depend upon temperature and angular momentum, we would like to measure the angular momentum of the fissioning system, which we measure by low energy gamma ray multiplicity detector. So keeping this in mind, so we designed and built a very nice 4-pi spin spectrometer to measure the angular momentum of the nuclei, and that was transported and coupled to the recoil mass separator at Inter-University Accelerator Center. And we did a lot of measurements, and I shall be primarily drawing from our efforts to measure the ER cross sections using gas field magnetic separator HYRA, hybrid recoil analyzer, and evaporation residue getter spin distributions using TIFR 4-pi sum-spin spectrometer. So this is the 4-pi sum-spin spectrometer in its full glory in my lab, right where I am sitting right now. And this thing, when it is on the beam line of the TIFR pelletron facility, and it is measuring low energy gamma rays along with, in conjunction with, the high energy giant dipole resonance gamma rays. And when the same thing has been transported to, this is just the Monte Carlo simulation of the response of the spin spectrometer. I need not go into the details of it, but this is the most of our experimental facility, where you see now this 4-pi spin spectrometer is dwarfed by this huge beast, which is more than 10 meters. This is the hybrid recoil analyzer at Nuclear Science Center. So the nuclear reactions are taking place at the center of this 4-pi spin spectrometer in this sphere. And the evaporation residues are filtered out through these combinations of electromagnetic devices, and they are brought at this focal plane where you see MWPC is written, multi-wire proportional counter. And in addition, we, in conjunction, in coincidence, we measure the number of the low energy gamma rays from which we find out the angular momentum. So this is basically the experimental setup, and I can tell with a fair amount of satisfaction that this combination of recoil mass separator along with 4-pi spin spectrometer is possibly the only of its kind in the world, and we have generated enormous amount of very interesting results. So what we have tried to do by these measurements, we have tried to understand the role of shell effects, whether shell effects play any role in the survival of the nucleus or its fission, role of entrance channel mass asymmetry, I talked about it earlier, role of the barrier heights, and role of the fusion-fission hindrance, which is some kind of quantum viscosity. So a lot of work has been developed, come out of this contribution, of this collaboration, and all these systems are here. I have actually no time nor intention to go into the details of this measurement. I would just like to summarize that what have we learned from these measurements. So a large number of systems have been studied, and a large body of new data, especially spin distribution data, have been generated. What do these measurements and results tell us beyond the obvious interpretations? So what they tell us is this. It's a very difficult ballgame, and it's so there are a lot of uncertainties with the different physical observables like barrier height, nuclear level density, viscosity, etc. So we need there is a need of reducing the parameter space to have a put realistic limits in the statistical model calculations, to carry out systematic analysis of global data, fission fragments, evaporation residue, neutrons, charged particle, high energy GDR gamma rays. Please note that no one group does all these measurements. So it should not happen that for the same system, different groups do different measurements, and with different codes they analyze and they arrive at different results. That's not acceptable. To arrive at the similar conclusions while using different phenomenological approaches, to reproduce the data with the same set of parameters irrespective of the analysis package. So that is basically what we have learned. So with this, I just want to draw from two very recent measurements which have been done in the last 2 years, and I will just try to talk about them. So what are those systems we have tried to study? We have tried to study two nucleus. One is a heavy nucleus, 186 platinum, by bombarding 32 sulfur beam on 154 samarium. And the other is a very heavy system. It is 32 sulfur plus 208 lead, forming 240 californium. Why you want to do this? What is the primary difference between them? You see, if you look at the heavy system, it's a heavy system, so it will undergo fission, but it will also survive fission. So some of the cross sections will go into the evaporation residue channel. And that basically means I am probing both inside and outside the saddle. It will be clear shortly what I want to mean by that. In the potential energy surface, there is a barrier, and then there is a saddle inside the pocket. The system gets trapped inside the pocket, and while fissioning is splitting, it moves on top of the saddle point and moves toward the scission point. So in this kind of a heavy system like 186 platinum, the system is both inside the saddle and outside the saddle. However, for a very heavy system like 240 californium, it is almost entirely fissioning, 99.99%. And therefore, I am basically probing only the saddle to the scission path. So this way, I can actually see the dynamics inside the saddle and outside the saddle and try to see whether the viscosity that we are trying to study is different in these two different parts. So this is clear from this picture, as I was trying to say. This is a very simple-minded one-dimensional projection of the potential energy surface. The nucleus is a compact object inside the pocket. It moves the flux towards the saddle point. It assaults the barrier and then rolls down at the scission point. It breaks into two. This is basically the thing. So now let us show me some of the results from the sulfur from samarium nucleus. We need not go into the details. These are very involved measurements. And you can see on the left side in the table, a lot of beam energies above the barrier at which we carry out this measurement. And then on the right side, this two-dimensional plot, you can see a blob. This is basically the focal plane of this hybrid recoil analyzer where we have detected the evaporation residues, and from that we can find the cross-section of the evaporation residues after putting suitable efficiency corrections. And we also measure the angular momentum, the spin distribution of the nucleus. And finally, on the right side, on the bottom, you will see the cross-sections. These are absolutely new, fresh data. This have not been done before. So we get the cross-section. So when we get the cross-sections, we have to do the analysis and understand what actually is happening. So the first thing is that without jumping on a model-dependent calculation, there is something which should come out straight away in a model-independent way from just the experimental measurements just after the data reduction. And that is a very interesting thing I show you here. You see on this plot, the red points are our measurements, which have been done for the first time. But the same nucleus, 186 platinum, was also populated some years ago by another group, also from India. We was not knowing that time. And then they measured, but their target projectile combination was very different. Highly symmetric compared to our asymmetric system of sulfur and samarium. It is 48 titanium plus 138 barium. And you see the distinctly order of magnitude different in the evaporation residue cross sections. So this is one very important thing, and it shows the clear demonstration of the role of entrance channel in the mass asymmetry. Now we want to go ahead and do the analysis using whatever is at our disposal. So basically, as I said earlier, it's a two-pronged strategy. We use statistical model analysis, and also we do dynamical model analysis. Now, I am talking about some very simple things here. The things are rather, we have developed a very involved statistical model code, but I'm just talking of the basic fundamentals of it. So we in the calculations, we do not do the calculations for the spin distribution of the cross sections. We put the real experimentally measured values, because as you have seen, we have measured the cross sections, so we know the cross sections, and this fission cross section plus evaporation residue cross section gives me the total fusion cross section, which we put in the calculations. We put the spin distribution, which we have measured in our experiment using the TI 4 pi sum spectrometer. We try to take care of the nuclear level densities using a very realistic formalism. We include viscosity, but that is more or less by hand. And we try to look for the temperature and spin dependent of the barrier height. And then once we do that, all these things have been also shown in our earlier work from Stony Brook Grace, which in somewhat recent time I have summarized all this in this paper, in the Pramana paper. And so I want to just show you that this is the spin distribution. This is the spin distribution experimentally we have determined from our analysis. Then you put a gate on different angular momentum domains, and we try to do the calculations. And these are the different formalisms from the level density, temperature dependent and spin dependent level density formalism. So as I said, there are various parameters. I mean, that barrier heights, there the viscosity, etc. So one should not actually try to just feed the data. One has to really see what are the different weight factors that you can attach to the different things, because all of them are playing a role. In this particular case, I'm trying to feed the data or reproduce the data by varying the barrier heights, and you can see we can do that fairly, but we also know what is the error associated, and that is associated with the width of these barrier heights that I show in the plots. Similarly, once that is done, I try to play the viscosity, and you can see what kind of viscosity value that we are getting. So at this stage, we feel that we also do some dynamical calculations. These calculations are primarily done by one of our collaborators from Russia, Professor Avazbek Nasirov, what is called the DNS model, or dinuclear system model. This is a pretty involved model. But one very important thing that I want to draw your attention to in this is that it turned out from this dynamical analysis that incomplete fusion also plays a role. What do you mean by that? You look at the cartoon. 18 oxygen is being bombarded on 93 niobium, and we are talking as if 18 oxygen will fully amalgamate with 93 niobium. But that doesn't happen. One particular channel is that maybe a little bit of tweak, one particle, maybe an alpha particle goes out of it, and the final compound nucleus is not 111, but 107. So in the calculations, and while we reproduced our data, it was found that this kind of role, a little bit of incomplete fusion channel, also plays a very important role. So these are some of the potential energy surfaces, and I need not go into the details of this. But the important part is this, that you see on the top, you have the spin distributions, which have been reproduced by these DNS calculations. And you see here, the experimental data is beautifully reproduced by the solid black line, which is the dynamic model DNS calculation. Now, the important thing is that if you only consider complete fusion, that is, no incomplete fusion is happening, then you can reproduce the data to some extent up to 140 MeV or so, but after that it doesn't. But as you switch on the other possibility of a little bit of incomplete fusion, that is the red line, then lo and behold, if you add them up, you beautifully reproduce the data. And trust me, we have been able to reproduce other data also by this. Now, what does it mean? So far, I was going on the premise that a full fusion takes place and then the fission is happening. Or fission is not happening, we are producing evaporation residues. But we have seen a little bit of incomplete fusion, that amplitude also plays a role. So we have to then, therefore, not only the evaporation residues, we should in a future measurements try to measure the charged particles also and do a full kinematical analysis to prove beyond doubt that this DNS model is correct. So this is one of the most important takeaways that we have shown in our paper very recently. And the last part, and I guess I have still some time. So what I'm talking, I will just go and to the very heavy system, which is 240 Californium. Now, this system, unlike the previous system, has been studied earlier. I, during my postdoctoral days, studied it to understand the giant dipole resonance gamma rays from this heavy system. Actually, 30 years ago, Birger Back and Mary Tang, they had exhaustively studied the fission fragments because that was the low-hanging fruits. But the evaporation residues were never been studied. In our studies of this nucleus, where we measured the giant dipole resonance gamma rays, we actually found a certain value of the so-called Kramer's viscosity parameter. And I was always intrigued to see whether if we measure the evaporation residues, which is a much more complicated problem for the obvious reason, it's a very low cross-section, then whether we can actually produce the data by the same viscosity parameters. And so by viscosity a little bit, so these were our very early measurements of GDR decays, and where we try to find the viscosities parameters by measuring the GDR gamma rays in coincidence with the fission fragments. And we realized that most of the gamma rays are coming basically from the saddle position point. And this is basically the Kramer's formalism. I will quickly go through that. As you can see, from the left, the nucleus, the flux is assaulting the barrier, and then it rolls down. And then you can calculate by Bohr principle, Bohr theory. But actually, it was a pioneering work went unnoticed for 40 years by Kramer, who actually showed that basically the width can come down because of the so-called viscosity, which of course he treated classically. But then we have tried to implement this kind of thing with more modern dynamical approaches, like this kind of a transient effect, which depends upon the barrier height and the temperature. That means if the temperature increases, most of the flux of the compound nucleus will straight away go onto the saddle and will not remain in the pocket. So anyway, these are basically just some of the glimpses of the underlying theoretical analysis that we carry out. But I will just say that also the important thing, what is this viscosity? Or is it a one-body mechanism or a two-body mechanism? If it is a two-body mechanism, then you can imagine that it will have a strong temperature dependence. And if it is a one-body mechanism, it is basically like the two system is fissioning, and basically the nucleons, one body is colliding with a moving potential well. So these are some kind of phenomenological approaches to understand this thing, and they will have different dependencies, and one body viscosity will not have much temperature dependence. So we just try to do these measurements. I am almost at the last minute of my talk. And then we bombarded sulfur on 208 lead, and we've produced 240 californium, and we just as you can see, this very, very small little bit of data which is there. This is a very, most of it is almost fissioning. And if we extract after all the efficiency corrections, we actually get the cross sections. But as you can see, the error is associated, is quite large, and we definitely want to carry out these measurements in more detail with a longer beam time in future. So that brings me at the end of this talk. It is a pleasant duty to collaborate, to thank my close collaborators. This is a picture of Ranjan Sarial, who is my former PhD student, who's this work, what I said, from the kernel of his PhD work, and now he's a postdoc at Gran Sasso. And also to my collaborators from Internal University Accelerator Center and Punjab University, and my long friend and collaborator, theorist, Professor Awaz Begnasirov from Russia. So let me sign off at this point, and I can take questions. Thank you very much.
Perhaps if Professor Bhasin deems it fit, we could now have the Q&A session.
Yes, I think Professor Haridas has a question.
How reliable is this saddle point that Bohr and Wheeler introduced in 1939? And are there systematic ways of improving the saddle point approximation?
Oh, yes, of course. I mean, there's been enormous. I mean, I'm happy that you asked. I mean, I couldn't go into all these details there. So what are the on the slides, I was basically showing a single one-dimensional point. But what actually happens that we do multi-dimensional calculations to get the what's called Rauthian, or the potential energy surface. And so it is actually, one should not really think in terms of a one-dimensional barrier. It is a multi-dimensional thing. There are valleys and there are ridges, and the compound nucleus is formed. And this barrier is also continuously kind of under fluctuation, because it is a temperature dependent, it's a spin dependent. So basically, you imagine you create this potential energy surface, and then the flux is moving. And then it looks for, it's exactly, imagine the meandering of a river through these hilly areas. So it looks for wherever it gets a path, it goes to that. And then, so this is done, there are involved calculations. So it is not just you calculate one barrier and you fix that, because it's a very dynamical thing. So the point is that as it moves through, what are the other, so barrier is, of course, I can fit most of that by data by just playing with the barrier. But that means basically putting all eggs in one basket. That will not be the right thing. We know the dissipative mechanism, which is basically coupling of the energy from this collective to non-collective degrees of freedom, also play an important role. So all these things have to be included in the analysis. And it's a very difficult problem actually to really say that exactly what is happening. But the first role is to get as much precise data that we can, and then try to also improve, calibrate the theory along with this against these advanced theories.
Thank you.
Yeah, Professor, I think Professor Panchpakashan has a question.
Yeah, please, Professor Panchpakashan.
Well, I really don't want to ask a question, but I was really very, very happy to learn that the IUAC, which is hardly 5 kilometers from my house, is deeply interested in the experiments that you're doing. I have frequent contact with Professor Pancholi, who goes there, who has been talking to me, but I never knew that fusion fission experiments are going on here. So next time you come, maybe we should get together there and discuss the whole thing. Thank you so much. Yeah.
That will be my absolute pleasure, sir. I look forward to our next meeting.
Sure. Yeah.
I just turn on my video to say hi to Indranil. Hi.
Hello, sir. How are you?
Okay.
Absolute pleasure. I just want to say that I showed Professor Mitra's this picture. This also adores my wall of my lab where I'm sitting right now, and it was such a pleasure that yesterday Ravi Rao was also showing some of the pictures from our meeting 15 years back. Any other question? Alok, is there any other question? I can.
Perhaps not. I don't see any raised hands, either via the cameras that are turned on or the icon.
What should I unshare?
Yeah. I guess